All right, today we are jumping headfirst into one of the wildest ideas in all of modern physics. We're talking about a serious scientific theory that might just let us break the ultimate speed limit of the universe and send messages faster than light. You know, from starships zipping between galaxies to instant communication across empires, faster than light travel is a staple of science fiction. But in the real world, well, it's pretty much considered impossible. So the big question is, did the laws of physics accidentally leave a bizarre little loophole open for us? For over 100 years, modern physics has been built on one solid, unwavering rule from Albert Einstein himself. Nothing, not a single object, not a signal, not one bit of information can travel faster than the speed of light. It's the law. But as it turns out, maybe some laws are meant to be broken. And that's where things get weird. The key comes from the strangest place in all of science, quantum mechanics. Because when you get down to the tiny scale of atoms and particles, the universe seems to play by a completely different rulebook, one that seems to totally clash with Einstein's nice, orderly cosmos. And look, this isn't just some random shot in the dark. This whole idea of breaking the light barrier comes directly from the deepest, most confusing puzzles right at the heart of quantum theory itself. So our guide on this wild ride is the philosopher of physics Shan Gao. In his work, which, by the way, is published by very serious places like Cambridge University Press, he makes the case that the secret path to faster-than-light communication is actually hidden inside two huge problems that have been driving physicists crazy for decades. And here they are, the big two. First, what even is the wave function? Just think of it as a cloud of possibilities for a particle. It tells you all the places it could be. But is that cloud a real physical thing? Or is it just math we use in our heads? And second, what's called the measurement problem. Why does that fuzzy quantum world suddenly snap into one single concrete reality the instant we try to look at it? Okay, this idea of collapse is absolutely crucial. Before you measure a particle, its wave function is just this big smear of potential. But the very act of looking at it forces it to pick one. That instantaneous jump from a cloud of maybe to a single, definite here is the collapse. And Gao believes that's the key that unlocks this whole thing. You know, the brilliant physicist John Bell totally nailed how absurd this problem is with this amazing quote. He's basically asking, what counts as a measurement that makes this collapse happen? Is it a detector? A cat? A scientist? The fact is, nobody knows. And that mystery is exactly where Gao begins to build his case. So, on to the first part of Gao's argument. To solve these mysteries, he starts by making a really bold, really fundamental claim about what the wave function actually is. This slide is great, because it really lays out the two sides of the debate. On one side, you have the epistemic view, which says the wave function is just a reflection of our ignorance. It's just what we know about something. But on the other side, the ontic view says, no, the wave function is a real thing, physically out there in the world. And Gao? He doesn't hesitate for a second. He's all in on the ontologic side. He says that for any of this to make sense, the wave function can't just be some idea. It has to be a real physical thing. This is the absolute foundation for everything else he proposes. And this is where it gets really wild. He says that this real thing is something he calls random discontinuous motion. So forget about particles moving in smooth lines. Gao says a particle is actually constantly randomly teleporting from one spot to another, so fast that it just looks like a blur. And that blur, that is the wave function. Okay, so if the wave function is this real thing made of particles literally jumping around, what happens when you measure one? This is where we get to the logic of how to actually send that faster-than-light signal. So let's walk through this step by step. First, you take two entangled particles, the ones that are mysteriously linked, where what happens to one instantly affects the other, no matter how far apart they are. Because they're linked, they share a single wave function. So, second, when you measure particle A, boom, you collapse the entire wave function. And if that collapse is a real physical thing happening, then particle B, light years away, has to react instantly. This suggests there's some kind of universal now that connects them, a preferred frame of reference. And right there, that's the bombshell. Einstein's entire theory of relativity is built on the idea that there is no universal now. His whole point is that time is relative, A universal clock that ticks the same for everyone, everywhere? That shatters a core pillar of modern physics. But Gao argues, hey, if you take quantum mechanics seriously, it's a conclusion you can't really avoid.
So, if this instantaneous connection really exists, how in the world could we actually use it to send a message? Well, Gao has proposed two very different and equally fascinating ways.
All right, the first method is, well, it's pretty out there. In his earlier thinking, Gao suggested that consciousness itself might be the missing piece. It's a seriously speculative idea that connects the mystery of quantum measurement with the mystery of consciousness. The idea is that maybe a conscious mind can somehow perceive the difference before and after a collapse in a way that no machine ever could, effectively seeing the signal directly. Now, the second method is a lot less philosophical and a lot more, brass tacks physics. Gao argues that in a lot of these collapse models, the process isn't perfect. When you force a big spread out wave function to suddenly pinpoint itself in one spot, it should, theoretically, release a tiny little puff of energy, a little heating effect. And here's the game plan for how you'd use it. A sender on one side of the galaxy decides to make a measurement that causes a really big collapse. This would create a slightly bigger heating effect at their friend's particle on the other side. A smaller collapse, less heat. And just like that, you've got a binary code. More heat could be a 1, less heat could be a 0. Instant communication. The only trick? Building a detector sensitive enough to pick up that unbelievably tiny change in temperature. So whether it's through consciousness or a tiny bit of heat, if this is actually possible, the implications are, and I am not exaggerating, reality-altering. It would change literally everything. I mean, just stop and think about it. Communication that isn't just fast, it's instant. And because of how entanglement works, it would be totally unhackable. It would force us to completely rewrite Einstein's theory of relativity, and it might even suggest that consciousness plays a real functional role in how the universe works. Now look, it's really important to remember, this is a theoretical proposal. We are on the absolute bleeding edge of physics here, built on ideas that are still being furiously debated. But what it is a serious attempt to solve some of the deepest paradoxes we know of. And that kind of leaves us with one final big question. Is this theory a sneak peek into how mind-bogglingly strange our universe actually is, or is it just proof that when it comes to understanding the quantum world, we're really only just getting started? And you know what? That's what makes this whole thing so incredibly exciting.